All right, this is question number 23. And let's see what it says. 41% of U.S. women consider reading as their favorite pleasure time activity. In a random sample of 50 women, would it be unusual, by mean and standard deviation, to find that 12 women considered reading as their favorite pleasure time activity? Well, let's see what we have here. We have 41%, which we know is like P, 0.41%. And it says we have a random sample n equals 50. And we want to know, is it considered unusual for 12 women to be their favorite, for 12 women to find that reading is their favorite pleasure time activity? Well, when we have n and p, then we should probably check to see if this is a binomial. So let's see. Some of our requirements. We need a fixed number of trials, which we do, 50. We need to make sure that they're independent. So let's see. If we did 50 divided by 0.05, let's see what we get. Oh, we get 1,000, which is clearly less than all women. U.S. women, I guess. So that's fine. Independent's good. The probability remains constant. It does. P equals 0.41. And there's only two outcomes. It either is their favorite activity or it's not. So yeah, this is binomial. Okay, so let's see here. We would say this is binomial. And so what we can do is we can find the mean using the n times p, and then the standard deviation is the square root of npq. So my mean is going to be 50 times 0.41, which equals, let's see, 20.5. And then our standard deviation would be the square root of 50 times 0.41 times 0.59, because that's 1 minus 0.41. Okay, and that's going to equal, 3.5. So if we want to know if something is unusual using mean and standard deviation, then we would take the mean minus 2 sigma and mean plus 2 sigma, and let's find out what numbers would be considered unusual, right? Well, mu minus 2 sigma, this is going to be 20.5 minus 2 times 3.5, and that equals 13.5. And then mu plus 2 sigma, 20.5 plus 2 times 3.5, this equals 27.5. So what we're saying is, let's see, let me do a number line here. 13.5, 27.5. So in the middle, usual. And then on the outsides, unusual. Right? Okay. So where does our number says, would it be unusual to find that 12 women consider reading as their favorite pleasure time activity? Okay, well, let's find out. Where does 12 fall into this? Well, 12 falls about here, right? That's 12. So it would be considered unusual, right? This is unusual. Usual. Unusual. So we would say it is unusual. Okay. All right, let's see. What do we have next? Number 24. A carpenter measures his work carefully, but his measurements are subject to some naturally occurring error. His measurements on average are off by 0.1 centimeters with a standard deviation of 0.09 centimeters. Find the z-score for a measurement that had an error of 0.25 centimeters. All right, so z-score, the formula for that is x minus mu over sigma. So let's see here. My mean, it says on average, right? So off by on average 0.1 centimeters. Oh, and then we have standard deviation of 0.09. And then his measurement was 0.25 centimeters. So my mean is 0.1. The standard deviation is 0.09. And x is 0.25. So we just simply plug these numbers in. 0.25 minus 0.1 divided by 0.09. Now, if you're going to type this all in your calculator at once, just make sure you put some parentheses. Oops. Some parentheses around your numerator here. So, z is going to equal 1.667. So this is going to be your z-score. I usually round to 2 decimal places, but others 3 decimal places, I guess. Now, I guess let's, we'll just go ahead and leave it 3 decimals to be consistent. Okay, interpret the z-score. So what does this mean? That a measurement of 0.25 centimeters is going to be 1.667 standard deviations above the mean. Okay, so a measurement of 0.25 centimeters. Sorry, a measurement, let me say, that has an error. An error of 0.25, that is an important distinction, of 0.25 centimeters is 1.667 standard deviations above the mean. I like that. There we go. All right. Next. An urban economist wishes to estimate the proportion of Americans who own their home. What sample size should be used if he wishes to estimate to within 5% with 96% confidence? Okay, what sample size? When you see that, you know that there's 2 formulas that estimate sample size. And the question is, do we have a prior estimate or not, right? So it says he wishes to estimate the proportion of Americans who own. Well, we don't have a prior estimate. So no prior estimate, which would have been p hat. So we use the formula n equals 0.25 times z alpha over 2 divided by e squared. Okay, so we need to find these things. Well, we know that alpha is 0.05. And let's see. Oh, no, I'm sorry, not alpha. What am I saying? E, my margin of error, estimate to be within 5%. So my E, there we go, is going to be 0.05. There we go. And then my Z alpha over 2, I'm going to find from my formula sheet where my confidence level, so I'm going to say C level, is 0.96 or 96%. Okay, so that means that my alpha is going to be 0.04 and well, you know what? let me see. I'm going to have to find, I guess, my formula sheet to look at for this. But, yeah, okay. So we may not be able to find this one from the formula sheet. So we've got sea level is 0.96, which means my alpha. All right, so my alpha is going to be 0.04 because that's the difference between the confidence level and 1. And then alpha over 2 is 0.02. And so our critical value is going to be z sub 0.02. And we find this on, the z-scores are on the bottom row of the table. So this is going to be 2.054. Okay. So we had to do a little extra work here, but that's okay. We can handle that. So let's plug in our stuff to the formula. N equals 0.25, which is 2.054 over 0.05 squared. Okay. And when we solve all of that, we get 421.8, which we should always round up, right? Always round these things up. Always round up. So n is going to equal 422. So, this, the always round up is only for the sample size stuff, right? We're not going to do that for everything else, but even if this was just slightly more than 421, we have to round up to 422 because we need to have, if we don't round up, for example, if I rounded down, even though in this case I wouldn't naturally round down, but let's say I had 421.2, and we would normally round that to 421, but that wouldn't be a big enough sample size to get 5% within 5%, right? My margin of error needs to be 0.05. Well, if I left that at 421, what we said was 421.2 is the smallest, absolute smallest you can have. Well, because we can't have a 0.2 person, you have to round up to the next one, right? Because we're looking for the very smallest sample size we can have to have this estimate to be within 5%. Okay, so you have to round this up. This is the only thing, though, that we're going to round up like this, like nothing else. We don't do this on anything else. Okay, let me see if I can pull up the formula sheet so I can show you where we got this z alpha over 2. So let me pause for a minute. Okay, so I've pulled up the formula chart, and here in the bottom, where we had the t distribution, if you look here at the top where it says 0.02, okay, then we follow that all the way to the very bottom. This is your z's right here, and this is where we got that. Oh, I can't circle on this, but right down here, you can see, well, you can't even see my, oh, there you can. It won't let me write on this, but this is where you can see that 2.054. That's where we got that for that last problem. So we went up here where we had the 0.02, and then the very bottom is the z. Okay. All right, so let's look at number 26 now. A random sample of college students was asked to record how many hours they sleep per night during final exams. In 22 students, the mean was 5.77 hours with a standard deviation of 1.72 hours. On average, are college students getting significantly less than 8 hours of sleep each night during final exams? So it says, on letter A, find the point estimate. Well, since we're dealing with means here, okay, then we know that the, this is for means, right? It says in here, mean. So when you see that, you know your point estimate for means is just x bar. So x bar is going to be 5.77. This is given to you in the problem, okay? I mean, that's all you have to do for that. But you need to know that the point estimate for means is x bar, okay? The point estimate for proportions is p hat, okay? It's a very important distinction. If the confidence interval is 5.01 to 6.53, interpret the confidence interval. Okay, so we've done this a bunch of times. We are, where's our confidence level? Well, how do we know what our confidence level is? Oh, well, I noticed that it doesn't have, it's supposed to say 95% right here. Let me check my, let me check my stuff really quick. Let me pause. All right, so I've gone and checked my issues here, and yes, this should be, this should say if the 95% confidence interval, which now is updated on my other things, so I'm sorry that it's not written on here. Let me go ahead and see if I can maybe just do that. Okay, so now that we can see the confidence level, which is kind of important, now it says we are 95% confident that the population mean what is our population mean talking about? The mean is number of hours they sleep each night during final exams. So the population mean number of hours slept by college students during final exams is between 5.01 and 6.53 hours. Okay. Draw a final conclusion. Are the students getting significantly less than 8 hours of sleep? Justify your answer. I would say yes, because even on the high end of our interval, that's a fairly significant difference between, so 6.5 hours versus 8 hours. I mean, even with that, I would say that, yeah, they are getting significantly less. So, since every number in the interval is below 8, then I would say they are getting significantly less than 8 hours of sleep. During finals. There we go. All right. All right. Next. How could the confidence interval be made narrower? Okay, so if we want to narrow that interval, then we can increase our sample size, or we could decrease the confidence level. If you make your confidence level less, like if you're less confident, then you can have a more narrow interval, right? The more confident you are, you're going to have a wider interval to cover more numbers, because you're saying that you're really confident it's between these two values, so you're going to have to give a wider interval, right? But if you're not as confident, then you can go with a more narrow interval, so we could decrease the confidence level. Okay. Let's see here. Number 27. If a confidence interval for a mean is 23.7 to 25.2, find both the point estimate and the margin of error. What are the proper symbols for these numbers? Okay, once again, highlighting the fact that it says it's for a mean. So for point estimate for a mean, okay, so the point estimate is going to be X bar, and it's going to be the average of these two numbers. So the number right in the middle, right? And so what we would do to find that is we would add 23.7 plus 25.2 and then divide by 2. That's how you take the average, right? Or the mean, I should say. So X bar equals 24.45. Okay, that's halfway in between those two numbers. Okay, now the margin of error, we use capital E. And you can do one of two things. You can take the upper end of your confidence interval and subtract off your point estimate, which is what I usually do. Or you can take these two numbers, subtract them, and then divide by 2. That'll give you the distance. So the margin of error is the distance from your, okay, so here's sample mean in the middle. Here's your upper bound, and then here's your lower bound, right? Margin of error is this distance from here to here. Okay, so you can do it however you like. You can find the whole distance, right? From here to here, and then divide by 2, and that's going to give you half the distance. So however you want to do that, I will just take 25.2 and subtract 24.45. So my margin of error would be 0.75. Okay. So let me go ahead and box those. There's that and that. There. Okay. Number 28. If a confidence interval for a proportion is 0.157 to 0.202, find both the point estimate and the margin of error. What are the proper symbols for these numbers? Okay, well, for point estimate for proportions, okay, so now for a proportion, right, that's a very important distinction. So point estimate for this one is P hat. And again, you'll find the same way. You're going to do 0.157 plus 0.202 and divide by 2. So P hat is going to equal 0.1795. And then the margin of error, which is E, we're going to do, here, let me write it underneath here. E equals 0.202 minus 0.1795, which gives me 0.0225. Okay, so point estimate. Okay. Oops. Next page. We're getting there. Page 17 now of 25. We're going to make it. We're going to make it. All right. In a random survey of 3,611 adult Americans, it was found that 542 had made purchases on their smartphone. What is the point estimate for the population proportion of adult Americans who make purchases on their smartphones? Report this estimate with the proper symbol. Okay, so proportion, point estimate. Those are my keywords here. And so what I'm going to say is P hat equals. Now, P hat is equal to X over N. So that's the part out of the total, right? So in other words, we want to know the part, which is the people that did make purchases on their smartphones out of the total number of people that were surveyed. So the total number of surveyed people is 3,611, and 542 of them have made purchases on their smartphones. So to find P hat, we're going to take 542, divide that by 3611, and we get 0.1501. So p hat equals 0.1501. That's the proper symbol there. Okay, if a 90% confidence interval for the population proportion of adult Americans who make purchases in their smartphones is 0.14 to 0.16, interpret this interval. We are 90% confident that the population proportion of adult Americans who make purchases on their smartphones is between 0.14 and 0.16. Now, you could also say between 14% and 16% if you wanted to. We would say percentage instead of proportion. We would just say we are 90% confident that the percentage of adult Americans who make purchases on their smartphones is between 14 and 16%. So you could state it that way if you'd like. I will say that I think this is like a super low number. I feel like this is not accurate. I mean, I feel like everybody makes purchases on their smartphones. I don't know, just saying. But at any rate, this is what the data found, right? Okay. Letter C says, can we conclude that more than 15% of adult Americans have made purchases on their smartphone? No, because our interval is so on the heels of saying that we could say this is 14%, 16%. So we could have done it like that. Here we could have said percentage instead of population proportion, right? So we could have done that. So when we say percentage between 14 and 16%, no, we can't conclude that more than 15%. No, because some numbers in our interval are less than 15%. Okay, because it could be 14%, right? That's included in our interval. Okay, how could the confidence interval be made narrower? Okay, well, I think we just asked this, right? We could increase the sample size. So increase, or we could decrease the confidence level. Okay. All right. Let's see which one we're on next. Number 30. Tests of hypotheses basics. Okay, it says you believe that your friend has an unfair coin that returns heads too often. Write the null and alternative hypotheses. So this is interesting because you're not seeing actual numbers here. But when we're talking about a coin toss, we know that you have a 50-50 chance of getting heads or tails if it's a fair coin, right? So what you want to test is the null hypothesis is that the proportion would be equal to 0.5. So proportion of heads, right? And then we want to know if the alternative here is, are we getting heads more than half of the time, more than 50%, right? So greater than 0.5. And we want to see if that is the case, right? So that's how we would set up that hypothesis test. Which of your hypotheses will you assume to be true? Well, the null. We always assume the null to be true until we find evidence to support otherwise. Assume the null true. Okay, which is p equals 0.5. Now, which of your hypotheses are you trying to support? We are trying to support the alternative, right? We're trying to find enough evidence to support our claim. Alternative H1, P greater than 0.5. Because we think that their coin is unfair, right? So that's what we're trying to find evidence to support. In 40 tosses of the coin, 30 of them came up as heads. You calculate the probability of obtaining at least 30 heads in 40 tosses as 0.001. What is the probability called in your test of hypotheses? Well, this is the p-value, okay? So 0.001 is the p-value. Okay, so we've calculated this probability, and let's see. So out of 40 tosses, we would expect that, 20 of them would come up heads, right? Because that's what we see when we have a fair coin. I mean, theoretically, right? But 30 of them came up as heads. So this probably tells us the likelihood of witnessing a sample of 40 random tosses with a result as high as 30 heads or higher is 0.001. That would be, okay, that's what this is telling us. Now, the next question, letter E, says, what decision should you make regarding the null hypothesis? Well, it depends on what we've chosen to use as our alpha. The default is 0.05 if you're not given one. In any case, most of them doesn't really matter, but the p-value is very low. So since p is less than alpha, then we would reject the null hypothesis, right? So let's see. Let's say let alpha equal 0.05. But even if it was 0.01, we would still be less than that, right? So my p, which is 0.001, if we let alpha equal 0.05, then p is less than alpha, and therefore you would reject the null. Okay, so what decision should you make regarding the alternative hypothesis? Well, we would support the alternative hypothesis, support H1, which says that P is greater than 0.5. Are the results of your hypothesis test statistically significant? Well, let's see. I would say yes. Anytime you are rejecting the null hypothesis, you're getting results that are statistically significant. So, yes. Okay, does it seem likely that the coin is unfair? Yeah, I would say yes, because we found statistically significant evidence to support our claim, right? So, yes. It is most likely that the coin is unfair. It is likely that the coin is unfair. Okay. Statistically, yes, since we rejected the null hypothesis. That J looks ridiculous. Oh my gosh. Let's try this again. Better. Okay. Let's see here. Number 31. A statistics student heard that an individual's arm span... Let me see where I'm at on time. Okay. Arm span is equal to the individual's height. To test this hypothesis, the student used a random sample of 10 students and obtained the following data. Okay. Write out the null and alternative hypotheses necessary to test at a 5% significance level if height and arm span are significantly different. Okay, so here's our keywords. 5% significance level. I wouldn't say necessarily it's a keyword, but we do need that information. Significantly different. So that's going to tell us the way we're going to set up our hypothesis test. So we want to know if these are related to each other, right? So we have student number. This looks like a matched pairs test, right? Because we have students and we're matching up their height and their arm span together. So this is a dependent matched pairs means. So make a little note here. This is matched pairs. Okay. And so we would set up our null hypothesis as mu sub d is equal to 0. And here we want to know if the difference is not equal to 0. So that's what we're looking at, because we're seeing if they are significantly different. So that dependent matched, this is dependent, right? Dependent matched pairs. And that sub d is for like the difference, right? That's what that d means, the difference in the means. And so that's how we would set this test up. And this is on the formula chart in chapter 11, specifies that this is how you write your null hypothesis right here. So, I mean, that's on your formula sheet, right? Okay. Use the computer output to answer the questions. So look at this right here. The test statistic is t equals, let me maybe highlight this, maybe blue. This right here is going to be your test statistic, negative 0.3924. And the p-value is 0.7039. So these are like appropriately highlighted or labeled, I guess. This is your p-value. Okay. This is your sample size right here, n. X bar is your sample mean, and S is your sample standard deviation. Okay. What conclusion should be made about the null hypothesis? Well, let's see. Our p-value is quite large. So it is our alpha. Let me make a little note here. Well, alpha was 0.05, right? That's what it said, 5% significance. Your p, so let me compare this. 0.7039 is definitely greater than 0.05. So p is greater than alpha. Do not reject the null hypothesis. So what conclusions should be made about the alternative hypothesis? We would not support the alternative hypothesis. Do not support the alternative. Okay. So final conclusion, does the sample provide enough evidence to support that arm span and height are significantly different? No, not enough evidence to support that claim. No, there is not enough evidence to support, that height and arm span are different. Height and arm span are significantly different. Okay. Does this prove that arm span and height for an individual are equal? No, it just means that we did not have enough evidence to support the claim that they're different. So it does not prove that they are equal. Okay. No, we just don't have enough evidence to say they are different, to claim they are different. Okay. Let's see here. Where are we at on time? Okay. I'm wondering if I should maybe do this one in the next video. I mean, this is like a full full page here. I guess I could go ahead and do this one now. Okay, it is believed that 85% of Americans eat salad at least once per week. A nutritionist suspects that the percentage is higher than this. She conducts a random survey of 200 Americans and finds that 90% of them eat salad at least once per week. Write out the null and alternative hypotheses necessary to test her suspicions at a 5% significance level. Okay, well, let's see here. Where are we dealing with means or proportions? That's the real first question we need to answer. And it says percentage in the problem, right? So we're seeing the word percentage, which means that I'm going to be dealing with proportions, okay? So I already know that my parameter here, this is parameter is proportion, which is P, okay? So we're going to put P's here. And we do equals for our null. And what are we equaling? So we're saying that the statement, like the status quo, right? What we're assuming to be true until we find evidence to support otherwise, is that 85% of Americans eat salad at least once per week. This is going to be my null hypothesis. Well, we always, of course, write this as 0.85. And we want to know if this is, so what did she say? She wants a random survey to find that. Oh, higher than this, right? She thinks it's higher. So we're going to put greater than there, higher, okay? Now, how many Americans in her sample eat salad at least once per week? Well, it tells, let's see, what do they tell us? They found random survey, so that's N equals 200. And it says 90% of them eat salad. That means your P hat is 0.90, right? So, or 0.9. So, if I want to know how many people eat salad, well, I would say here's my formula, right, for P hat. It's X over N. Well, if I plug in what I have here, which is 0.9 equals X over 200, I need to solve for X. Well, I can do that by multiplying both sides by 200. Let me multiply by 200 here. And these are going to cancel out. So 200 times 0.9 is 180. So X equals 180. Alternatively, you could use this formula, X equals N times P hat, which is really what we did here by multiplying the N over. I just did it a little differently. That's fine. But if you would rather look at it like this is good. So X equals 180. Okay. That's how many Americans in this sample said they eat salad at least once per week. Sorry. Use a computer output to answer the questions. The test statistics. So in this case, because we are talking about, we've got Z here. Z is going to be my test statistic, and I'm going to round that to 1.980. And the p-value is 0.0238. So test statistic, that's that one here. And then the p-value, okay. All right. What conclusion should be made about the null hypothesis? Well, my p-value is, now what did it say to test at? 5%, right? So let me make a little note here. Alpha equals 0.05. Okay, so P is 0.0238, which is less than 0.05. So if P is less than alpha, then we say that we reject the null hypothesis. And what conclusions should be made about the alternative? We would support the alternative. Okay, final conclusion. What can we conclude about the percentage of Americans who eat salad at least once per week? That we found enough evidence to support our claim that it is greater than 85%. So, let me see. We conclude that the percentage of Americans who eat salad at least once per week is higher than 85%. Okay, a 95% confidence interval for the percentage of Americans who eat salad at least once per week is 85.8 to 94.2. Does this support your conclusion about the null hypothesis? Justify your answer. Well, let's see here. I would say yes, because 85% is not within that confidence interval, right? So, we're saying that we're 95% confident that the percentage is anywhere from 85.8% to 94.2%, right? So that would be, yeah, that's going to be higher than 85%. So I would say yes, since all numbers in the interval are higher than 85, we would reject the null. Okay. All right. If the percentage of Americans who eat salad at least once per week is higher than 85%, by how much is it higher? Do you think this is a practical difference? How could the hypothesis test be improved? Well, let's see. We have this interval right here, right? So if I say 85.8 minus 85, that's 0.8%. Versus, let's see, and then 94.2 minus 85 is 9.2%. Okay, well, this may or may not indicate practical significance, right? If it's higher by 9.2%, then that seems like a large enough number to say it's an important difference, but only 0.8% doesn't seem like a very important difference at all. So there's a problem with this study because the sample size was too small to have enough information to decide. So to make this hypothesis test better, we would use a larger sample. So let's see. Do you think it's a practical difference? May or may not be a practical difference. May or may not be practical. Let me see, actually. Practical difference. Let's see. How could the hypothesis test be improved? Use a larger sample size. Okay. I think I'll end this video here.